I would like to now welcome Darren Ray, Principal Climate Change Analyst at the SA Department for Environment and Water, to share with you his presentation. Thank you so much.
So there's a few people in the audience who know me from my work with the Bureau of Meteorology. So trained initially as a forecaster back in as a graduate, Bureau's graduate program in 2002 in weather forecasting, moved into climate after a few years, and I was senior climatologist in the Bureau of Meteorology in South Australia. But I've since moved out of the Bureau a few years ago and now working with the Department of Environment and Water in climate change, and also in the middle of a PhD on climate as well. So I want to start off with a very deliberately, very simple diagram. So really, I just really want to get across this point. I chose the simplest diagram I could find. How does rain form? We're looking at two key ingredients that we need for rain. We're looking for moist air, and we need it to be rising up. So just keep that in mind. So this is all about, in terms of when we talk about rainfall in Australia, we're looking for moisture sources, and we're looking for mechanisms that that lift that rain up. So people would be familiar with the variability in the Pacific Ocean with El Nino events under the broad name El Nino Southern Oscillation, variation on year-to-year basis between La Nina and El Nino events. And so reasons they impact rainfall is from two reasons. They change the wind patterns, changes in the oceans and wind patterns change the ocean temperatures around Australia, and they also impact the atmospheric circulation. So in La Nina events, we get stronger trade winds, and the warm water tends to pile up, warmed up by the oceans, piles up in the Pacific warm pool around Indonesia, Philippines, etc., Papua New Guinea, and we get more moisture coming off the oceans into the atmosphere, and that can rise up and form into rain. And the atmosphere circulation also, in the Walker circulation across the Pacific Ocean, supports that increased convection rising up. And so we get wetter conditions in La Nina events, and the opposite occurs in El Nino. So we see weaker trade winds, the ocean temperatures cool off, we get less moisture, the atmosphere reforms, tends to sink down more, inhibiting rainfall. So you know, that we can think of this broad background state that we see causes variations in the sources of moisture for Australia, and also what's going on with the atmosphere as well as whether it's tending to sink up or and support rainfall and cloud formation or act against that. Importantly for South Australia as well is the influence coming down from the Indian Ocean to the northwest, and we see variability on a similar sort of year-to-year basis in the Indian Ocean dipole. And so once again, we see the variations in those in the moisture sources that feed it across Australia. And in the negative phases, we get warmer waters around off to the northwest, and the atmosphere tends to rise up more. So that's supporting rainfall. And the negative phase, positive phase of the IOD tends to do the opposite. So we get the atmosphere sinking down more and less moisture coming off the oceans. So this is driving, so I'm talking about year-to-year variability. So I'm going to get into climate change in a second. I'll just touch on this briefly. This is variations in the wind patterns in the mid-latitudes that are important for southern South Australia. So something called the southern annular mode. I'll talk about that in terms of what we've seen in terms of this summer in particular. And so it is influenced by increasing greenhouse gases, cause it to be more positive, which means the weather patterns tend to contract a bit more further south, and that tends to support higher pressure over in terms of stronger subtropical ridge over southern Australia in the positive phase. And so greenhouse gases make SAM more positive, but ozone depletion also impacts SAM as well. So there's a springtime and early summer influence from southern annular mode, which impacts weather patterns and has been impacting weather patterns over the last few decades. So, and I'll touch on that a little bit more later on. So this sort of diagram on the left here, you can see the average impact on rainfall in the positive phase. So, and it varies in time of year. So it has a does tend to drag down a bit more moisture in the tropics, make things wetter in some parts of Australia in summer, and a little bit in spring as well. And then in autumn, winter, it tends to have a drying effect in positive SAM and wetter in negative SAM values. But I'll come back to a little what we're seeing with that. So it's another little wrinkle in terms of influences, influenced by human activity through ozone depletion as well as greenhouse gases. But just quick on climate change. So one of the key points I always make when I talk about it is there is direct observational evidence from satellite and ground-based instruments that measure the amount of heat going into the atmosphere, coming down from the atmosphere and going out of the atmosphere into space over decades now. And there's been repeated work looking at the changes in the energy balance over recent decades. And so this is a recent paper, came out a couple of years ago, and just showing that we are seeing direct observational evidence that increasing greenhouse gases are stopping more heat going to space. So this is basically like nail in the coffin for anyone who's a little bit skeptical about climate change or tries to, or thinks that maybe it's a natural cycle, because it's clearly not. So I just want to hammer that point home that, you know, there is this direct evidence. So if you're talking to people about this, you can point to this sort of thing and knock that on the head really quickly. Also, global climate models. So I'm going to talk about about modelling of future climate, and one of the key points is that there's been lots of work. We've had projections around for a number of decades now that go back to the 1970s, and there's been lots of work reviewing that, showing okay, how well does that modelling capture what's been going on since those models were introduced from the 1970s, 80s, 90s onwards. And key point is they capture basically the general physics of the climate system really quite well. So, you know, and this is another, you know, piece of confirmation or strong evidence that the effect of greenhouse gases is well understood and captured in a broad sense by the models. Now it gets a little bit trickier, and this is what we're all about here today. Is I'm going to talk about what when you get down to the local scale, it does get a little bit more tricky and a little bit more complex. So I'm going to be going through some of that detail. But essentially, one of the key things in a warming planet is hydrological cycle intensification. So the oceans warm up, they release more heat. The atmosphere warms up, that can hold more heat, and so basically that intensifies the hydrological cycle generally. And there's lots of evidence of that going on. And one of the supports for that for Australia is, so we've got the map on the right there of the trends in sea surface temperatures around over Australia in the last few decades. And there's, you know, some pretty clearly everywhere is warming up with more moisture around Australia. And the atmosphere, if you look at some evidence of what's going on with how much atmosphere is trends in levels of atmosphere or moisture in the atmosphere, there's lots of work showing that there is increasing amounts of moisture in the atmosphere as a result of that. And so there's some work on the left there that at a global scale showing trends in water vapor levels in the atmosphere. And I've got some precipitable water as a measure of how much water is in a column through the atmosphere on the right there over the Adelaide region. And I've split that up for November to March and April to October. So just showing 2 different times a year. So it's basically a bit of a stronger trend there in November to March. So spring, summer, amounts of moisture in the atmosphere. So with all of that, you might suggest we might be seeing increasing rainfall extremes with the increasing moisture over the Adelaide region supporting rainfall. Now, if you look at observed daily scale rainfall extremes for Adelaide, so I've got Adelaide Airport observations. So the annual daily maximum rainfall amount each year. So what's the highest daily rainfall total that's been recorded each year at Adelaide Airport? It's got a reasonable record back to the 50s. You do see some multi-decadal variability. So I've got a 10-year mean through that. And so periods there where you do see a bit of increase in the events, but if anything, there's on a what's still a relatively short record, there's a slight trend downwards. So we're actually not seeing at this scale, at daily scale, we're not seeing, clear trends of increasing rainfall extremes on a daily scale in the Adelaide region. But there's some multi-decadal variability. So this is variability where there's more La Nina events that happen through the 70s. It happened again a little bit in the late 90s and 2000s, and then La Nina events in the 2010s as well. So there's a bit of a signal, some multi-decadal variability in there, and that's related to variations in the occurrence of La Nina events and El Nino events. So what's happening? Well, so we've got as I mentioned, the two things. So increasing moisture so you're looking for moisture, but you're also looking for the atmosphere to rise up, or that moisture to be rising up to form rain. And so in a warming planet, basically the Hadley circulation expands, and we see changes in the atmospheric circulation, which mean we're seeing more subsidence or sinking down of the atmosphere in the mid-latitudes from that Hadley circulation. So warm air rising up, moves towards the poles, sinks down in mid-latitudes and forms a subtropical ridge. And so I've got some sea level pressure from a reanalysis data set on the right-hand side there for the Adelaide region, showing we're seeing increasing air pressure at the surface. And so this is basically reflecting these changes in the atmospheric circulation. So across southern Australia, we're seeing changes from the warming of the planet in the atmospheric circulation as an opposing influence on rainfall formation. And we see that in rainfall totals, on average rainfall, but also in the extremes as well. So there's sort of two mechanisms in the mid-latitudes opposing each other, more moisture, but we've also got the atmosphere opposing that. So another sort of little bit of evidence there. So how much is the atmosphere rising up or sinking down? And it's tending to sink down more over the Adelaide region. So it's just sort of highlighting that at that broad scale, we're seeing opposing influences on rainfall changes. Now it gets a little bit more interesting at the sub-daily scale, and so a lot of our extreme rainfall events are driven by thunderstorm activity. And so very local scale, so we're down to sort of a few kilometres scale, convective activity that can generate intense rainfall, more typically the sort of hourly time frame. And that is a lot trickier and as someone has forecast a number of, when I was working originally as a meteorologist, very tricky to forecast, but often a contributor to extreme rainfall events on very short timeframes. Now, there's a lot of evidence showing that there is a difference in the intensification of rainfall extremes from the daily scale to the hourly scale. So the daily scale rainfall extremes are in many places increasing at about a 7% per 1 degree of warming, so the Classius-Clapeyron relationship. But the hourly scale, they're intensifying about 3 to 4 times more quickly than that. And so there's been some various analysis of rainfall extremes evidencing that. And so we can see a map of some of that done, once again showing the difference between the daily scale and hourly scale. So blue's increasing intensity and red is decreasing intensity. So there's a bit of a tendency over southern Australia for decrease or staying much the same in terms of rainfall intensity at the daily scale in this work. But at the hourly scale, we see much more widespread intensification of rainfall extremes. So that's really where it gets tricky. Now, what complicates that in terms of trying to understand that is we don't have, we've got, records of daily rainfall that go back for some locations and back to the 1800s. For hourly observations, we really only have lots of locations, maybe 20, at most 30 years worth of hourly rainfall observations. So it makes it really hard for this sort of work in terms of trying to understand trends and the possible influence of multi-decadal variability in this as well. So where does that leave us in terms of projections? So the projections I'm working on in Department of Environment and Water. So in South Australia, we had the Goida point-based statistical downscaled work. I've been working on this NARCLIM data set, so NARCLIM 1.5, and it's some downscaling to 10 kilometre resolution across this red domain and 50 kilometre more broadly from global climate modelling for 6 global climate model and regional climate model combinations, and that produces daily values of rainfall and temperature with some bias correction in there as well, that go from 1951 out to 2100. So we get some useful data in that. There's a projections viewer that Belinda mentioned, and that shows trends in average temperatures and extreme temperatures and average rainfall. Now, did a fair bit of work trying to apply AR&R methodologies to the daily data set to try and produce something sensible, but really struggled with that. So we're not there yet in terms of having useful information on rainfall extremes available out of the projections, and that's going to be really one of my main focuses is this year, is to try and get there with that. And the other focus is doing the work to introduce this new 4 kilometre resolution prediction data set from NARCLIM 2, which is being run at the moment in New South Wales. But what does it look like in terms of average rainfall? So we've got 6 different downscale GCM, RCM combinations. So these are the different projections from different modelling combinations available out of NARCLIM 1.5. We've got the percent change of Adelaide rainfall compared to 1956 to 85 period for the medium emission scenario. So the blue is actually the observed change over the period 1986 to 2005. So that's a commonly used climate change projection baseline period. And then they've got what the model said. So they run the models for the historical period, what the model said would have happened over that time in the orange, and then the future projections from each of those models over 30-year periods into the future. So key thing out of this is there's some mixed messages in there. And so the temperature projections are pretty solid and pretty clear in terms of trends. The rainfall projections, the trends are a little more mixed, is probably a fair thing. But I mean, the clearest thing we see out of this is there is a significant drying projected in the sort of late winter, spring period out of the projections. And we actually see some recovery of winter rainfall in some of the models, and so there's some very subtle variations in there that are probably down to the influence of things like ozone recovery and southern La Nina mode and influences like that, which you know, we've seen ozone depletion over the last few decades, and we're expecting ozone recovery over the next few decades. So lots of different competing influences in there. But so I've ran the maximum daily rainfall total out of the projections and compare that to the observations. So the observations are in the grey for Adelaide Airport, and the closest grid point out of the modelling and all those different models. And really, I mean, the key message in there, the decadal variability, the signal that we're seeing in there, the actual observed rainfall is bigger than what we're seeing in the projections. And that's probably because the models are underdoing the oceanic variability around Australia. But there's not really any particularly clear, strong trend showing up. There's a slight signal for some intensification of rainfall with this measure. Now, unfortunately, this is about the best we can do for projections of rainfall extremes at the moment. So, and this is an area of active research in terms of, you know, the Bureau and other research groups, and how do we do something better with this? And, you know, we very much understand that there's need for better measures of this, and trying to match up the climate change projections and getting something useful out of it is a pretty active area of work at the moment. One of the things is with the modelling getting down to that sort of scale of thunderstorms, we're now down to what we call a convection permitting modelling scale. And so there's the modelling, so the NARCLIM stuff in NARCLIM 2 is 4 kilometres. That's starting to get down there, but probably not quite enough. And so we're probably still like a generation of modelling away from incorporating convection permitting modelling into the downscaling process. So, you know, it's probably, we've probably got maybe 5 years of work, or maybe even a bit more, before we can actually start getting some really robust climate projections coming out of the global climate modelling, going through the downscaling, and then coming out into information that can really start supporting the rainfall extremes decisions. So yeah, I mentioned NARCLIM 2 will improve things, but it's still some way to go with that. It's just showing all the different range of models that we've got available, and there's the evaluation process that they go through with that. And the models all do have different biases, so the different GCMs. It's important this evaluation process in terms of evaluating which one's best for Australia. So just to complicate the picture further, we saw El Nino this year, but it was unusually wet. So what was going on with that? One of the interesting wrinkles with that is we saw changes in shipping rules, which is producing less pollution and cloud over the oceans, with this big drop-off in declining sulfur emissions from shipping, because they changed the rules on ship fuel a couple of years ago. And that's certainly at least one of the reasons why we're seeing record ocean temperatures in many parts of the world at the moment. And that's been supported lots of moisture coming across Australia, but also southern El Nino mode was positive. So we had ozone hole that was really quite low over last spring and through this summer, and that contributed to positive SAM values, dragging down more moisture. So it just points to this combination of, the warming oceans are really important, and if you've got the right mechanism supporting that moisture to come down over Australia, that can really contribute to significant rain. And that gets a bit interesting if we look at what we're expecting this year, and this might be possibly the most interesting thing for people, useful thing out of today from me, is that we're looking at the possibility. Now, it's not set in stone yet. There's still some mixed signals in the modelling, but there's some strong signals there of the possibility of a strong La Nina event developing through winter and spring this year. And that looks like it could well be supported by record warmest ocean temperatures around Australia. Now, that combination of La Nina, which would support rainfall formation, and record ocean temperatures, presents a really high risk of flooding this year. And I suggest possibly even record flooding as we go through late winter, spring, and into summer this year. So, and there's lots of other things I could say, but there's AMOC ocean circulation shutdown, which complicates the picture over the next few decades. And the questions around whether we'll end up with El Nino conditions or La Nina conditions over coming decades as the predominant thing. There's some still significant questions around that, as more uncertainty in there. And I'll just mention sea level rise. So because there's lots of work in the last couple of decades on climate change tipping points, and work on ice sheets in Greenland and West Antarctica, indicating there's really high sensitivity there, higher than anticipated, more water going into the oceans from ice sheets, from Greenland, for instance. And so this IPCC low likelihood high impact storyline, which ramps up sea level rise more significantly than we've been anticipating for a while, is starting to look a little bit more likely, which has got implications for coastal infrastructure and planning of that over the next sort of 150 years. So I'll finish up there. So just some summary points. There's clear evidence of ocean warming, increased moisture availability. Daily rainfall extremes are certainly increasing in tropical areas, subdaily strongly increasing in many areas. But if you look at the Adelaide region, daily rainfall extremes are not showing any particular trend, with possibly some multi-decadal variability, despite that increased atmospheric moisture, but we've got those opposing mechanisms going on. The drying is certainly projected, but we're in a place where there's a lot of work needs to be done still. And as I mentioned, this might be the most important thing I talk about today. Watch out for rain in the second half of this year.
Thank you, Darren. I really enjoyed that. I think it's important to know what's coming at the second half of this year. I think everybody was sort of expecting El Nino to continue. So it's really interesting to see how the global climate models are changing in such short periods of time as well. And it's obviously extremely complicated, and it's great to know that there's the science sitting there waiting to be used. And I think our next two presenters will hopefully demonstrate how we can apply some of that scientific understanding to the research that they're undertaking.